Welcome to the Deep Dive. We're the show that cuts through the noise, stacks up the sources, and really tries to distill complex topics into the key insights you need.
That's the goal.
And today we are diving deep, plunging into a world of, well, invisible forces, flows, fields twisting. It's all about how things move in these really fascinating, interconnected ways.
Yeah, when you think about meteorologists trying to model a hurricane,
Yeah.
I mean, the complexity there,
Right.
or engineers designing, say, how water flows through pipes and pumps, or even just gravity,
Yeah.
how it keeps us here, keeps planets orbiting. These are not simple things to describe with the calculus most people learn first.
Absolutely not. Our usual tools, single, double, even triple integrals, they don't quite cut it for these really dynamic real-world situations.
But you need something more.
Exactly. We need a whole new set of tools. And that is our mission for this deep dive. We're tackling vector calculus, primarily drawing from the Stewart, Clegg, and Watson text, trying to give you a kind of shortcut to understanding this really powerful field. We'll unpack the core ideas step by step, aiming for, clear explanations, intuitive analogies, practical applications, trying to show how it all connects to the world around you.
Hopefully some real aha moments along the way.
Let's hope so.
Yeah.
So, where do we kick things off?
Well, first things first, we absolutely have to get our heads around the idea of vector fields.
Okay.
Think of them like this. They're functions, but instead of just spitting out a number at each point in space, they assign a vector.
Meaning magnitude and direction.
Exactly. Magnitude and direction at every single point. It's how we mathematically visualize and describe things where direction matters, like wind patterns, ocean currents, the pull of gravity.
Yeah.
Things that change depending on where you are.
Gotcha. So those weather maps showing wind, with all the little arrows indicating speed and direction everywhere, that's a perfect example, right? A velocity vector field.
Precisely. Or, how water flows in a river or air moving past an airplane wing. Every point in that space gets an arrow telling you where and how fast something's moving right there.
It's not just for movement, though.
No, not at all. We also have force fields. The classic one is gravity. Imagine Earth at the center. The gravitational force vector at any point nearby points right towards the center, and its strength drops off really fast the further you get.
An inverse square law, right?
That's the one. And electric fields, Coulomb's law, they work in a very, very similar way. These fields let us understand forces acting across empty space, which is pretty amazing when you think about it.
And visualizing these sounds key, sketching them out, drawing the little arrows at different points to get a feel for the flow.
It helps build intuition, definitely. You might see vectors swirling, maybe pointing inwards, but honestly, for the big picture, computers are invaluable.
Right. They can plot thousands of vectors, scale them properly, let you really see the whole field.
And there's a really important type of vector field we need to mention. Gradient fields.
Okay, gradient fields. What makes them special?
They're special because they actually come directly from a simpler function, a scalar function one, that just gives you a number at each point, like temperature or, say, elevation on a map.
Ah.
If a vector field is the gradient of some scalar function, we call it a conservative vector field. And that scalar function, that's its potential function.
And gravity is one of those.
Gravity is a perfect example. It's conservative. And its potential function is related to gravitational potential energy.
And visually, what does the gradient tell us?
This is cool. The gradient vectors always point perpendicular to the level curves of the scalar function, like contour lines on a topo map.
Okay, so perpendicular to lines of equal height, for instance.
Exactly. And not just that, their length tells you how steep the function is right there. Longer vectors mean the level curves are packed closer together, a steeper slope. The gradient points in the direction of the steepest uphill climb.
That's a really neat connection, scalar info generating vector direction.
Yes. So now we have these fields.
Yeah.
How do we measure things along paths within them? That brings us to line integrals.
Right, because usually we integrate over intervals, like on the x-axis or maybe flat areas.
Exactly. But what if you want to integrate along a curve snaking through space? That's what line integrals are for. They were actually developed way back to handle problems involving fluid flow, forces, electromagnetism, real physical stuff.
So the basic idea, is it like chopping up the path?
Sort of, yeah. Think Riemann sums, but along a curve. You break the curve into tiny little pieces. For each tiny piece, you take the function's value there and multiply by the length of that tiny piece, the arc length. Then you just sum all those contributions up.
Okay, so we're integrating along the curve itself. That little d's piece is like a tiny step along the path.
Precisely. It's an infinitesimal bit of arc length.
And what can these tell us? What are the applications?
Well, they have some great physical interpretations. If your function f represents, say, the density of a thin wire bent into the shape of the curve c, then the line integral CFCED gives you the total mass of that wire.
Makes sense. Density times length, summed up.
Yep. Or, maybe even more fundamental, if you have a force field F, the line integral, territories if you otar, calculates the work done by that force as it moves a particle along that curve C.
Oh, work. Force times displacement, essentially, but integrated along a path.
Exactly. And the work can be positive if the force helps the motion, or negative if it resists it. Direction matters.
And you mentioned direction. Does the way you travel along the curve affect the answer?
Sometimes. For certain types of line integrals, reversing the direction flips the sign of the result.
Okay.
But for integrals with respect to arc length, that d's we talked about, the value stays the same. d's is always a positive length.
Interesting distinction. Okay, so these line integrals seem powerful, but maybe complicated to calculate.
They can be, but there's a beautiful simplification, a real game changer. The fundamental theorem for line integrals.
Okay, sounds important, like the fundamental theorem of calculus.
Exactly like it, but generalized. Remember how integrating a derivative f from a to b just gave you fb, fa?
Yep, endpoint values were all that mattered.
Well, this theorem does the same thing for line integrals. If, and this is a big if, the vector field f is conservative.
Meaning it's the gradient of some potential function, f, like we talked about earlier.
Correct. So if fs, then the theorem says the line integral akr EC is simply f endpoint, f start point.
Wow, okay, so the work done, for instance, just depends on the potential function's value at the start and end.
That's the magic. The actual path you take between those points doesn't matter at all. This is called independence of path.
That seems huge. What's the impact of that?
Oh, it's immense, especially in physics. Think about it. The work done by a conservative force, like gravity or an electric field, when you move an object along a closed loop, ending up back where you started.
The start and end points are the same, so f start would be 0.
Exactly. The net work done is always 0 for a conservative force over a closed path. This is a cornerstone of physics.
Yeah.
And it leads directly to the law of conservation of energy. Because it means that in a conservative field, the total mechanical energy potential plus kinetic stays constant. Energy isn't lost or gained just by moving around, as long as you account for the potential energy changes. That's why they're called conservative fields. They conserve energy.
That is a fantastic connection, a mathematical property directly explaining a fundamental physical law. So practically, how do we know if a field is conservative, and how do we find that potential function every other one?
Good questions. There are tests. For 2D fields, there's a quick check involving partial derivatives, basically, seeing if certain cross derivatives are equal. If fpi plus qj, you check if sprq.
Okay.
And if it is conservative, there's a method, often called partial integration, that lets you systematically figure out the potential function f.
And knowing phi makes calculating the line integral way easier.
Much easier. Instead of parameterizing the whole path and doing a potentially tricky integral, you just find f and plug in the endpoints. Big time saver.
Right, so we've got fields, paths through them. What's next?
Let's build another bridge. This time between line integrals and double integrals. That's where Green's theorem comes in.
Green's theorem. Okay. What's the connection it makes?
It connects a line integral around a simple closed curve in the plane.
Like a loop.
Exactly, a loop in the z-plane. And it relates that line integral to a double integral over the flat region inside that loop. It's like a doorway between the 1D boundary and the 2D area it encloses.
Another generalization of the fundamental theorem?
You could definitely see it that way. It fits the pattern. An integral of something derivative-like over a region equals the original function evaluated on boundary. It's the 2D version.
And practically speaking, why is this useful?
Well, sometimes that line integral around the boundary is just nasty to compute directly. Green's theorem lets you swap it for a double integral over the area, which might be much, much simpler.
So it gives you an alternative way to calculate.
Exactly. And one really neat trick is using it backwards to calculate area. By picking the functions p and q in the line integral just right, you can make the double integral part equal to 1dAA, which is the area.
Clever. So you can find the area of some region just by doing a line integral around its edge?
Yep. There are simple formulas like area ekis x tagadi. It's even the principle behind old mechanical tools called planimeters, used to measure the area of irregular shapes on maps.
Huh. That's pretty cool. Okay, so Green's theorem links line and double integrals in 2D. What about digging deeper into the vector fields themselves?
Good point. We need to introduce two crucial new operators that act on vector fields: curl and divergence. Think of them as specialized ways to differentiate vector fields, each revealing different properties.
Okay, first up, curl. What does that do?
When you take the curl of a vector field F, you get another vector field, denoted curl F or XF.
A vector output from a vector input.
Right, and it has a direct link back to conservative fields. If a field F is conservative, F is always 0, then its curl is always 0. Curl.
Ah, so if the curl isn't 0, the field definitely isn't conservative. A quick check.
Exactly. It's a necessary condition. And the converse is also true under certain conditions. If curl F equals 0 everywhere in a simply connected region, basically a region with no holes, then the field is conservative.
Okay, so mathematically it relates to being conservative. What about physically? What does curl mean?
Think about fluid flow again. If F is the velocity field of a fluid, curl F at a point measures the fluid's tendency to rotate or swirl right there.
Like little whirlpools.
Kind of.
Right.
Imagine putting a tiny paddle wheel in the fluid. It will spin fastest when its axle points in the direction of curl F. The magnitude of curl F tells you how fast it spins. If curl S kills 0, the flow is called irrotational. The paddle wheel wouldn't spin, it would just drift along.
Interesting. So curl is about rotation. What about the other one, divergence?
Divergence is different. When you take the divergence of a vector field F, written div F or ACUF, you get a scalar field, just a number at each point.
Scalar output from a vector input. Okay, and what does it measure?
It measures the tendency of the field to spread out or converge at a point. Think fluid flow again. Div F measures the rate at which fluid is expanding or compressing right at that spot.
So like if fluid is flowing outwards from a point.
If div F0, that point is acting like a source fluid is diverging or expanding away from it. If div F0, it's a sink fluid is converging or compressing towards it.
And if div F equals 0.
Then the fluid is incompressible at that point. There's no net inflow or outflow. Water is often modeled as incompressible. And there's a neat identity. The divergence of a curl is always 0. Div curl F equals 0.
So any field that is a curl can't have sources or sinks.
That's right. These operators, curl and divergence, give us powerful lenses to analyze vector field behavior rotation and expansion compression.
Okay, we've covered fields, paths, 2D regions. Let's venture into 3D properly. How do we describe surfaces in 3D beyond simple graphs?
Great question. Just like we use RT with one parameter t for curves, we use RUV with two parameters u and v to describe parametric surfaces. This lets us define much more complex shapes, spheres, cylinders, toruses, things that aren't just z if x, y.
So u and v are kind of like coordinates on the surface itself.
Exactly. Think of latitude and longitude on a sphere. Those are parameters u and v. As you vary u and v, you trace out the surface, creating grid curves on it.
And can we find things like tangent planes on these surfaces?
Absolutely. You take partial derivatives with respect to u and v, giving you two tangent vectors, ρ and rv. Their cross product, ρ x rv, gives you a vector that's normal, perpendicular to the surface at that point. That defines the tangent plane.
Okay, makes sense. And what about calculating the area of these curvy surfaces?
The intuition is similar to line integrals or double integrals. You imagine chopping the surface up into tiny little patches. Each patch can be approximated by a tiny parallelogram spanned by those tangent vectors ρ and rv adv.
And the area of that parallelogram involves the cross product.
Precisely. The area of that tiny patch is ρ x rv ddv. So to get the total surface area, you integrate this quantity over the domain of the parameters u and v area S. Juniority, ρ x rv dA.
And this works. Like, does it give the right answer for known shapes?
It does. You can use it to derive the classic formula for the surface area of a sphere, 4a2, beautifully. And there's a simplified version if your surface is given as a graph z equals fxy.
Okay, so we can describe surfaces and find their areas. Can we integrate over them too?
Yes. That leads us to surface integrals. We're extending the idea again. If you have a scalar function f defined in 3D space, URI FDS lets you accumulate the values of f over the entire surface S.
Like finding the mass of a curved sheet if f is its density.
Exactly like that. Mass of a thin sheet is a classic application. The calculation involves that ρ xrv factor again. ρ xrv dA. Now, you mentioned orientation being important earlier. Does that come back here? Absolutely crucial. For many surface integrals, especially those involving vector fields, we need oriented surfaces. We have to decide which side is out or positive.
Like the difference between a regular surface and a Mobius strip.
Exactly. A Mobius strip is non-orientable. It only has one side. But for most surfaces we deal with, like spheres or patches, we can define a consistent outward or upward normal vector n at each point. For a closed surface like a sphere, the convention is that the positive orientation means the normal vectors point outward from the enclosed volume.
Okay, so why is orientation so vital?
It's vital for surface integrals of vector fields, often called flux integrals. The flux of a vector field F across an oriented surface S is written AASFSEENIS,
Flux, like flow.
Precisely. It measures the net rate at which the stuff represented by F, like fluid or electric field lines or heat, is flowing through the surface S in the direction of the chosen normal N.
So if F is fluid velocity, flux is volume flow rate through the surface.
Exactly. Positive flux means net flow out, negative means net flow in. The calculation involves F through XRV integrated over the parameter domain.
And this is used in physics?
Hugely. Calculating fluid flow through a membrane, heat flow across a boundary, and critically, Gauss's law in electromagnetism relates the electric flux through a closed surface to the total electric charge enclosed within it. It's fundamental.
Wow. Okay, this is getting really powerful. Are there more big theorems connecting these ideas?
Yes, two more grand generalizations that tie everything together. Stokes Theorem and the Divergence Theorem.
Let's take Stokes' theorem first. How does it relate to what we've seen?
Stokes' theorem is like Green's theorem, but lifted into 3 dimensions. Green's related a line integral around a flat boundary to a double integral over the flat area. Stokes relates a line integral around the boundary curve C of a surface S in 3D space.
So the edge of the surface.
Right, the edge, or rim C.
Yeah.
It relates the line integral ICS F UDOU around that boundary to a surface integral of the curl of F over the surface S itself. SCS, a DRS, curl FFDS.
Whoa. So the circulation of F around the edge equals the total swirliness, the curl, integrated over the surface inside.
That's a great way to put it. The total spinning tendency across the surface adds up to the flow around the boundary. And importantly, S can be any surface that has C as its boundary.
Does that make calculations easier sometimes?
Often, yes. Maybe the line integral around a complicated curve C is hard. But if C is the edge of a simpler surface, like a flat disk, calculating the surface integral of the curl over that disk might be much easier.
And it gives more meaning to curl, right?
Definitely. It mathematically confirms that curl F acts like a circulation density. Integrating it over the surface gives the total circulation around the edge. It pins down that paddle wheel idea.
Okay, that's Stokes. What about the last big one, the divergence theorem?
The divergence theorem, sometimes called Gauss's theorem, is the final major piece. It connects a surface integral over a closed surface S, one that completely encloses a solid volume E.
Like a sphere enclosing a ball or a cube enclosing, well, a cube.
Exactly. It connects the surface integral of a vector field F over that closed boundary S to a triple integral of the divergence of F throughout the entire enclosed solid volume E.
So S is FUEDS equals ESA DVV.
That's the one.
What does that mean intuitively?
It means the total flux of F flowing out through the closed boundary surface S
The total net outflow.
is exactly equal to the sum total of all the sources, div F0 minus the sinks, div S0, distributed throughout the entire volume E inside. The total expansion compression within the volume manifests as net flow across the boundary.
And this helps with calculations too.
Oh, dramatically. Calculating flux often means integrating over multiple surface pieces, like the 6 faces of a cube. The divergence theorem often lets you swap that potentially complicated surface integral for a single, possibly much easier, triple integral of the divergence over the volume.
It really ties divergence to the idea of flux source density.
It absolutely does. It gives div F the concrete meaning of outward flux per unit volume.
So, these 5 theorems. The original fundamental theorem, the one for line integrals, Green's, Stokes, and divergence, they seem related.
They are profoundly related. That's the grand synthesis here. If you step back and look at all of them, you see this incredible unifying pattern.
That's the path.
In every single case, you have an integral of some kind of derivative on one side.
Like F area, which is related to curl F to if F.
Exactly. An integral of a derivative over some kind of region, an interval, a curve, a plane region, a surface, a solid volume.
Okay.
And on the other side of the equation, you have the original function or field,
Yeah.
FFBQ, FF again, evaluated only on the boundary of that region.
Wow. Integral of derivative over region and like function on boundary. That holds for all of them.
That's the amazing unifying theme. It allows us to move between dimensions, between integrals over regions, and evaluations on boundaries. It gives us flexibility, different perspectives, and often much simpler ways to solve really complex problems.
It connects calculus across dimensions in a really elegant way.
It truly does. From understanding hurricanes and fluid flow to designing systems, grasping gravity and electromagnetism, Vector calculus gives us the language, the toolkit, to precisely quantify and predict how our physical world behaves.
So maybe a final thought for you listening. Consider how these mathematical ideas, which might seem abstract at first, actually give us the power to map out and understand the invisible forces and flows shaping everything around us.
Yeah, every gust of wind, the heat flow in an engine, the interaction of charged particles. Vector calculus is the language underneath it all. What hidden dynamics, what flows or forces in your own area of interest might these principles help you uncover?
We really encourage you to, maybe revisit some examples, try to visualize these fields and flows, and just appreciate the sheer elegance and power of these theorems. They really do deepen our understanding of the universe.